Now I'm going to put on my radio announcer voice. Welcome to Chicago, Illinois quantum computing. Wait a minute. Let's start that again. Welcome to Chicago quantum. What do we call ourselves?
Quantum
Ron, help
computing,
me.
Chicago, Illinois, and beyond.
Welcome to quantum computing, Chicago, Illinois, and beyond. Today's, yes, today's presenter is Alicia Svetitsky. He is a scientific business development manager with Quantum Machines. And he's going to talk to us today about building the quantum control stack. Alicia, the floor is yours.
Thank you. Sharing my screen. Okay, so huge thank you to Barry for setting this up. He gave me a heads up. Oh, I should have. Okay, the date there is wrong. He gave me a
Close
heads up.
enough. Close enough.
Gave me a heads up that there might be like a large variety of backgrounds in the audience, different levels of knowledge about quantum computing. So I hope there'll be something here for everybody. So in quantum machines, what are we actually building in quantum machines? We're a company, first of all. That was an obvious, a for-profit company. In quantum machines, we don't build quantum computers. Okay, so when you look at a quantum computer, you've got the qubits on one end. On top of the qubits, you might have some optical elements, you might have cryogenics, sample holders, filters, and so on. Above that, you've got the control system, classical electronics operating at room temperature. And then on top of that, you've got software. So in quantum machines, we build the room temperature controllers. That's our focus. We've got some diversions in either direction, but really the core technology is about the electronics. And my mission today is really to convince you that that is the most critical component of a quantum computer. Okay. So feel free, by the way, to interrupt me at any time with questions or have those. I'd like to make this as interactive as possible. So just a snapshot about the company. We were founded in 2018. We now have over 250 customers throughout the quantum ecosystem using our technology. These customers are in academic institutions, national labs, startups, HPC centers, etc. Basically, throughout the quantum ecosystem, you can find our technology. We have over 160 people in the company. These include software engineers and FPGA people and so on. But we have a large team of physicists in the company, and everything we do in quantum machines is really 100% physicist driven. Okay, the end product is an electronics product, but the mission is quantum, so it's really driven by physicists. Neil, we're picking up a lot of white noise from your end. Can you mute please? Okay. So the outline of my talk is I'll present briefly of what real-time control is actually about, why this is different from what other control systems look like, basically what we do at quantum machines, and I'll present our product. I'm not selling anything here tonight, but just so we can get a little concrete. I'll talk about some applications of real-time control, and the purpose here, it's not just to check these boxes, it's really to build up an understanding of why real-time control is critical for quantum computing. And then finally, I'll talk about some challenges in scaling up. Because when we talk about quantum computing, we're not talking about 2-qubit experiments in academic context. We really want to talk about thousands and millions of qubits. So what challenges does that present for the control system? Okay, so what is real-time quantum control about? Let's look at a classical computer architecture. Okay, just a layout of a classical computer chip. It'll look something like this. Now, my question to you is, what would a quantum analog of this look like? If you've got a quantum computer, what would the layout look like? So this is pretty universal. Okay, it would look very similar to this. And the follow-up question is, what role do the qubits play? What do qubits actually do in a quantum computer? Now, if you think about it, qubits actually don't do much. Qubits are completely passive creatures. They sit there in a fridge or in a trap, getting zapped by pulses. Okay, every single gate that you see in a quantum circuit, you've got a quantum algorithm, every single logic gate that you see, it's actually a pulse coming from the electronics and zapping the qubits. Every measurement that you see, every processing, every feedback, every decision that you have to make in this algorithm, it's happening in the electronics, not in the qubits. The qubits function essentially as a memory. So in the quantum analog, you've got this, so if you want to look at the quantum analog of this layout, the qubits would be a piece of the data memory and arguably a piece of the ALU, but everything else here would be the electronics. The function would have to be filled by the electronics. So that is the challenge of quantum control. Okay, it's not about building a huge physics experiment and then having traditional electronics kicking it every now and then. We actually need the electronics to be tightly integrated with the qubits, and integrated, I mean in time. We want the electronics to be able to control the qubits, measure them, respond to measurements, and adapt on qubit timescales. So when we look at it at one of these renderings of a quantum computer, the focus would actually not be on the qubits or only on the qubits that are inside a fridge or an optical trap or whatever, but it's actually the electronics, the racks of electronics around it. The qubits should be thought of essentially as a memory. It's a memory that can enter all kinds of exotic states, but it's really just a memory at the end of the day. Okay, so we need electronics that can handle the requirements of quantum computing. So that was kind of an abstract presentation of real-time quantum control.
Alicia,
Now,
I want to just interrupt with one, maybe it's a half a comment, half a question. When we talk about the memory in a classical computer, we're talking about something that's more or less passive. It doesn't do anything. We take from it and we put to it. On the other hand, there's a certain amount of logic that qubits implement when we're talking about a quantum computer. I know that this is picking hairs, but I just want to.
No, that's great. Yeah. So I mentioned that it can also be thought of as part of the ALU. Okay, there is some element of computation that qubits implement when you've got interference on the qubit chip. But still, on the algorithmic level, like most of it is actually happening on the electrons. That's what I was saying. But you're right. It's not purely a memory. There's also an ALU component in there, but it's not sufficient. It's not the full ALU. You've got a lot of logic happening on the electrons. Okay.
Okay.
Cool. Okay, so this might sound a little technical, but it's really crucial to understand what we do with quantum machines. So physicists for many years have been using memory-based test and measurement devices. So test and measurement is it's a huge ecosystem. Basically, you're developing some new antenna, and then you want to test the antenna, so you get some very expensive electronics with high sampling rates and low noise and so on, basically to kick the antenna and see what it does. So these products are memory-based, and memory-based, I mean, if you want to play a pulse from one of these devices, you load a pulse into the memory of the system, and then when you trigger it, it's going to spit out the pulse. Now, that has limitations. For example, how big is the memory? What's the longest sequence that you can play? But also, what kind of feedback can you implement? If you've committed to a certain pulse in advance, it's not going to be able to adapt to what the qubit is doing in real time because it takes a couple minutes to upload a pulse. So it's great for testing out some new device, but it's not going to be integrated with the QPU. So we need something that's not memory-based. So we need a processor-based quantum control system. So a processor is something that can actually follow instructions in real time, and those instructions followed on the hardware level can operate on qubit timescales. So the way, if you have a processor, then first of all, you have a programming language, not simply defining pulses and times and so on. You have to have a programming language that'll show in the next slide. That language then gets compiled to a low-level instruction set, which is executed in real time. So ultimately, you'll have some box with SMA connectors that's sticking out, just like test and measurement products. But the difference is that behind these channels, you'll actually have a processor, a pulse processor, executing instructions, playing pulses, getting measurement results, processing them, deciding what to do next. All of this completely on the hardware level. When we say real time, we mean on the hardware level without going back to software. Because if you have to go back to software in the middle of a qubit experiment, by the time you get back to the qubits, they've lived and died 1,000 times. So we want to do everything on the hardware level. So how do we program this pulse processor? So the idea here, I'm going to give a kind of a high-level overview of a quad programming language. But the point here isn't obviously to teach anyone qua. It's also not really about the syntax. Rather, it's what is possible to implement in real time. And we said something is possible in qua, we mean that if you type this up, this will be implemented on the hardware level on the FPGA, if people here are familiar with FPGAs. Okay, so we don't want to implement these commands in software. We want these commands to compile to something much lower level so that they can run on qubit timescales. So in qua, we can play pulses. Okay, I want to play pulses to my qubits. I also want to measure my qubits. Now, the different qubits are measured in different ways. These measurements might involve demodulations, integrations. If we're talking about defect centers, you might want to count photons and time tag them. So we have all these capabilities on this instrument. We need to have classical operations. Okay, it's not just about test and measurement, playing pulses and measuring pulses. We need to be able to have classical variables that exist in real time that we can process in real time. Take some qubit measurement and then, oh, I'm jumping ahead there, but we need classical variables that exist in real time. And we can do math on these variables. Now we can use these classical variables that are in plain pulses. So if I want to change an amplitude or duration or frequency or a phase of an output pulse, I can use these variables when I'm generating my pulse. So it's already very different from a memory-based system where I commit in advance to what I'm going to play. Here, I can modify my pulses based on these parameters in real time. And I can feed these classical variables by measurements. So this kind of closes the feedback loop. I can measure a qubit. That measurement can then go into a classical variable that exists in real time, not on my computer, it exists on the instrument. Then I can do some math on that, and then I can use that result to generate my next pulse. So this is really tight feedback on hardware timescales. Next, we have control flow, which means decision making in real time. Okay, so if else branches, while loops, for loops, and so on. And finally, time control. Time control means I might have lots of different qubits and I'm implementing different protocols on each of them. One qubit, some of these protocols might be non-deterministic. I might have while loops that are implemented once or 1,000 times. Then at some point, I want one qubit to wait for the other qubit to be ready. So I might have real-time synchronization going on, something I couldn't know in advance. That's also something that the control system has to be able to manage. So if we take a step back now and look at quant, the most generic quantum experiment you can imagine is going to be some combination of these capabilities. You're playing pulses to the qubit, you're measuring them, you're calculating something based on that response, and then you're deciding what to do next. Deciding what to do next could mean I want to play this pulse from this channel, that pulse from that channel, depending on what I just measured. Or it could involve some kind of analog feedback. Analog feedback meaning changing pulse parameters based on what I just measured, track drift, and so on. So the most generic quantum experiments are going to be some combination of these capabilities. And just to stress this again, I've already said this, but I really want to emphasize this because this is really the whole point here. Everything here is happening on the hardware level. Typing up an if-else statement in Python is easy, but that does not happen on qubit timescales. We want to be able to implement these if-else branches and everything else here on the qubit timescale, the deeply sub-microsecond timescale. So I just have 2 slides now on the products. As I said, I'm not selling anything, but I do want to make this a little concrete because ultimately, when we build up quantum computers, this is what they'll look like from the quantum machines end. So the first product that we put out a few years ago is the OPX, the one you see here on top. A bunch of output channels and then a couple input channels for measurement. And the idea is that, as I said before, this might look quite generic from the outside, but the idea that on the inside you have the pulse processor, you've got the FPGA generating pulses in real time, generating these complex sequences in real time based on instructions, not based on memory, measuring what's coming back in the inputs, then processing that and making its decisions in real time. Now that's a baseband module that only goes up to 400 megahertz for the engineers in the crowd. So if you want to reach qubit frequencies, which are typically in the gigahertz range, you need to upconvert that. For that, we have a separate octave module. This is a module that has IQ mixers and local oscillators. It's a very traditional kind of product. There's nothing unique about it, like the OPX. The OPX is really something from the future. The octave is about convenience. It's a way of bringing the OPX into the gigahertz frequency range that superconducting qubits and spin qubits require. Now, we can scale these up. You can stack up a bunch of OPXs and it can function as one big unit. Here on the left, you can see a stack of 9 OPXs and 6 octaves that we delivered over a year ago. And when I say that you can stack these up and operate them as a single unit, it's not just about synchronizing these different channels. It's about being able to share information. You want to be able to measure a qubit on one OPX and use that for feedback from another OPX. You want to be able to shuttle this information in between them, not merely synchronize and have them trigger each other. You actually want, when you measure a qubit on one system, that information lives physically on one of these systems. You want to be able to shuttle this information around so that can really function as one big, gigantic real-time OPX.
And
Now, yeah, yeah.
why would you need more than one OPX?
So,
Why would when one of them communicates with the other and you're shuttling information around, what is the second one doing that the first one couldn't do? So that information needs to pass between them.
so they're playing pulses to different qubits, right?
Oh, I see. I
you
see.
you'll have a big stack of these, and you've got tons and tons of cables going from this system to a dilution fridge or some such. Okay, so different OPXs are talking to different qubits. So I measure these qubits, and that needs to affect my feedback on another qubit. That information has to reach the other OPX. And that's a very tough problem to solve, and that's one of the big challenges of quantum control, and that's one of our value props, really.
And now we have a question in the chat. Do kernel, OS, or compilers exist for QC?
I don't know enough about that to answer. Sorry.
So
Okay.
can we infer from the number of B and C connectors on these boxes how many qubits they manage per box?
Yes, so that depends on the qubit architecture. Okay, especially with superconducting qubits and spin qubits, it's a bit of a jungle. Some different qubit architectures require a different number of channels. You've got also couplers between qubits. How do you implement 2-qubit gates? So I'll just give you an example. With superconducting qubits, you might require simply one high frequency line per qubit. And with cross resonance architectures, you can also implement 2-qubit gates with those same drive lines. But other architectures also require low frequency flux line per qubit. Some 2-qubit gate architectures are implemented with their own control lines. So this really depends on how you build the QPU. There's no simple answer there.
Okay, and you mentioned that you're using FPGAs
Yes.
with gigahertz capability. Are the FPGAs synthesizing like microwave pulses, or are the microwaves generated from a generator and steered around the system?
Okay, great question. This is just one slide. I have another slide with our current generation, but in this for this slide, the OPX generates frequencies up to 400 megahertz, and that is completely digital on the FPGA. Okay, and then the up conversion is analog. The up conversion to gigahertz is analog. The octave is an analog product.
Got
The
it.
current generation. Okay, so this is that big stack that I showed of 9 OPXs and 6 octaves. Today we would not have offered that kind of solution. Okay, the OPX and octave are good for low scale experiments, small scale experiments, but for experiments that need very many channels, we've developed the OPX 1000. And the idea here is that it's this chassis-based system, and there are two species of modules that you can plug into this. One is a low frequency module up to 750 megahertz, and the other is a direct digital synthesis module that goes up to 10.5 gigahertz. So there too, you have an FPGA generating essentially the IF at 400 or 800 megahertz. We have a couple modes, and that gets digitally up converted to gigahertz frequencies. So you've got an FPGA on a relatively slow clock of about 250 megahertz, but then that plays after up conversion, that plays from a very fast DAC with a clock speed of 12 gigahertz.
So you send the lower frequency, what, like in to a classical phase lock loop frequency multiplier or something, and to get it up to higher frequency.
Not quite. I can't comment on that too much.
Okay, gotcha.
The idea is basically it's okay. I won't comment on that too much. Let's say that phase locked loops though are not a great solution because this noise accumulates, especially across devices. It's not a good solution when you're looking at scale if you want to synchronize very many channels. But the
Very
idea is that
interesting.
really
Thanks.
the idea to keep in mind though is that FPGAs are incredible, but they are relatively slow. So you want to do all the magic in some baseband and then up convert that, whether it's analog or digital. You're not going to have an FPGA directly digitizing, no playing. You're not going to have an FPGA competing with an AWG that plays at 100 gigasamples per second. The FPGA will operate more slowly and then will up convert that. So that's just like to put a face on some of these capabilities. Okay, so ultimately you're going to have some product like this, then you'll have cables going from here to the qubits, and I want to talk about what we can actually do with that. So um, I've got 5 examples here of what people actually do with real-time control in quantum systems. So this is an example of using real-time control not to implement some fancy algorithm, but to implement a very traditional Ramsey measurement, but very, very quickly. So a Ramsey measurement involves 2 pi half pulses separated by some delay, followed by a measurement. And if you sweep the timing in between the pulses and you sweep the frequency of the pulses, you end up with a 2D graph, a 2D plot as shown on the right. Now, this kind of plot used to take this specific lab about 10 hours to generate. And with the OPX, this acquisition time comes down to a minute. And I want to explain where that speed up comes from. So it's kind of a good intro use case. So if you're using an AWG, a memory-based system, every point on this plot is a different sequence, right? Because I need to actually upload a new sequence with a different spacing between the pulses, with a different frequency. So just uploading a new pulse, a new sequence each time to an AWG, that takes a minute or two. So I upload a sequence, then I play it 1,000 times for statistics and move on to the next sequence. And that way I acquire all this data eventually, but that's going to take hours. The OPS can generate these pulses in real time based on instructions. So I don't have this overhead of talking to the OPS and uploading new sequences to my computer each shot. I simply give it instructions. I say, this is what a Gaussian looks like, and I want you to sweep this from here to there, and I want you to sweep that from there to here. And it generates these unique sequences on the fly. So what the quad code actually looks like is what we see here. We've got the instructions to generate pulses. So I've defined a pi half pulse somewhere, and then I can set the frequency and set the time, the delay time in between pulses, and those are instructions. Okay, the delay time is not some list of zeros. It's simply hitting this instruction to wait a time t. What is that time t? It's taking it from one of the loops. I've got these nested loops. These loops are not being unwrapped ahead of time on my computer. And giving the OPS instructions to implement these loops, it has these real-time variables. As I showed in a previous slide, it's incrementing this variable and generating these new sequences on the fly. So these sequences might have, each one of these loops might run over 10 elements. It can run over 10 billion elements. The OPX doesn't care. Simply processing, churning through these variables, incrementing them, and generating new sequences on the fly. So you only upload a few kilobytes of information, just give it these instructions, and then it's good to go. You don't have the overhead of uploading a new sequence each time. Another speed up that we have is an active initialization, an active reset. And this is really something that's become quite popular in quantum computing. So I've got some transmon qubit. I've done something to it. I've measured it. I now need to initialize it again before the next shot. I just measured it. It's a 0 or 1. I need to be back in 0 before I take my next shot. So how do you do this? If you don't have real-time feedback, if you don't have real-time control, the only way to do that is simply to wait 10 times the qubit lifetime for the qubit to decay in thermals. So since everything we're doing here is happening within a qubit lifetime, that means if I'm waiting 10 times a qubit lifetime for the qubit to initialize, that means that 90% of the time I'm just waiting for the initialization. So however long my experiment is taking, I can make it happen 10 times faster if I can actively initialize the qubit. And that's what we have here. So we just measure the qubit. We know if it's a 0 or 1. And then we have a conditional pi pulse. What this means is if my qubit is a 0, I don't need to wait 10 times t1. I can just take the next shot right away. If I measured the qubit in the 1 state, I'm going to play a pi pulse to initialize it to the ground state, and then take the next shot. So you have to be able, this is the kind of feedback that you have to be able to implement quickly, because if it takes too long to evaluate and to evaluate this condition and play the feedback pulse, the qubit might decay on itself. Okay, and you want, and if it decays to the ground state before you play the pulse, then you're actually disrupting it and exciting it again. So you can't do this on softer timescales. And this is the kind of functionality that the OPX can implement with a latency of 120 nanoseconds. A deeply, deeply sub-coherence time. So say you've got a transmon qubit with a lifetime of 100 microseconds. So the initialization, a passive initialization could take a millisecond. Here we're doing that in 100 nanoseconds. So that's also a radical speed up in acquisition at the end of the day. And finally, this is a note for experimentalists. I don't know if we have experimental physicists here, but this is a very nice capability of the OPX, which is quite subtle, but also very powerful. We always put the averaging loop on the outside. Now think about that for a second. What do we do with an AWG? If you have a memory-based test and measurement product, you upload a pulse and then play it 1,000 times. That means the averaging loop is effectively on the inside. You define the sequence, and then you're going to play it 1,000 times. Then you move on to the next sequence, play that 1,000 times. And you don't really have a choice because of the overhead involved in uploading a new sequence each time. But what that means is that your data is then sensitive to slow noise. Because that means I'm looking at, I hope you can see my mouse. That means if I'm looking at the sequence to generate this point, and then I average over that point, then I move on to the next one, to the next one. By the time I get to the other side of the plot, the whole thing may have drifted. Okay, I got 1 over F noise, I've got some slow noise in my system. I'll see the smear in my data. When I put the averaging loop on the outside, I'm essentially taking one shot of the whole matrix, then another shot, then another shot, then another shot, and this whole thing averages out. It's only possible if the control system is agnostic to the order of these loops. It's generating a unique sequence each time, jumping from one to the next, and that way I'm not going to see any of this smear. That's kind of a subtle point, and it's mostly for the experimentalists in the audience, if we have any. So this example was about fast acquisition. You want to characterize a qubit. Is it going to take you 10 hours? It can take you 1 minute. Even though it's a very traditional kind of measurement that people have been doing since the 80s, you can do it much, much faster with real-time control. The next example is about embedded calibrations, not just fast calibrations. Say you want these calibrations not just to be executed on a time scale of a minute, you actually want to embed these calibrations in your algorithms. Okay, so you've got some algorithm that you're running, you now want every certain number of shots, you want to recalibrate the system without going to software. You want the control system to do that on its own. So what that requires is measurement of the qubit. Then you need some kind of real-time processing, some kind of calculation implemented in real time. And then you need analog feedback. Analog feedback means changing pulse parameters to account for what I just calculated. So can we do this in real time? Well, with Qua, we certainly can. And the way we calibrate the kind of drift on the left, so on the left, it's a Ramsey measurement over time of a transmon qubit. So if you look at a detuned Ramsey oscillation, a detuned Ramsey measurement of the qubit, so if it's on resonance, you just see a straight decay over time as it loses coherence. But if the Ramsey pulses are off resonance with the qubits, you actually get oscillations. So that's what we see on the left. And this the qubit frequency here is drifting over time. So the amount of detuning from the control sequence is itself drifting over time. So that's why the frequency on the left is drifting. And the way we can calculate this in real time, let's look at the let's look at the figure on the right. So if we sweep the frequency of a Ramsey sequence, not the time, but the frequency, we'll get these oscillations with maximal visibility when the drive is on resonance. And then as we detune the drive, the visibility goes down. So we can pick 2 points here on either side of the resonance. If the resonance is right in between the 2 points, we'll see the same amplitude. But if the qubit frequency has drifted slightly to the right, then we'll get an imbalance. And if it drifts to the left, we'll get an imbalance in the other direction. So we can do this 2-point Ramsey measurement to detect the qubit drift, and we also know which direction it's drifted. So we can take these measurements, we can do some PID calculation, and then we can correct the drive frequency, the control frequency. So this is an embedded calibration in the sense that it's not simply fast in the sense that we get the data quickly. It's that we actually have a control system following the qubit in real time. The qubits drift, okay, you calibrate the qubit, you pinpointed it in some million-dimensional parameter space. It's now going to start floating in that parameter space. With real-time control, we have the control system following it and staying calibrated on top of it. So the next example here, this is really a spectacular paper from NBI, the Niels Bohr Institute in Copenhagen. So this is from a spin qubit system. The previous examples were with the superconducting qubits. So here we've got a spin qubit, a double quantum dot in gallium arsenide, and a substrate of aluminum gallium arsenide. And the thing about aluminum gallium arsenide is that it has a nuclear spin. So the qubit in gallium arsenide is effectively coupled to this nuclear spin back. And the coupling drifts over time on a time scale of about 100 microseconds. And that causes decoherence. If you cannot account for the nuclear spin of the substrate, then the qubit then just looks like decoherence when you're measuring the qubit. And that's something that's going to drift on a time scale of 100 microseconds. Now, what they did in this paper, they characterized the coupling strength of the qubit to the spin back. And in order to be relevant, you have to do that quickly, because if you characterize it once, okay, 100 microseconds later, it's going to be someplace else. So you have to be able to characterize it quickly. And then and the way you characterize it is with this Bayesian estimation process. So basically, you have a list of guesses, and then based on measurements, you can assign a probability to each one of these guesses. And then you can pick most likely coupling strength to the spin back. And then once you've calculated that, you can feed that forward into your sequence. Then there are two things you can do there. One is you can decouple the qubit from the nuclear spin back. There's some rotating frame procedure to do that. And next, you can actually piggyback on top of it to implement two-axis control. Now, with superconducting qubits, it's very easy to do two-axis control. Okay, so what I mean by that is I can play a microwave pulse and rotate the qubit around the x-axis. I can just as easily add a phase and rotate the qubit around the y-axis. So that's two-axis control in superconducting qubits. With spin qubits, that's often not possible. Okay, you often only have one axis of control. If you do your sequence, it's going to rotate around one axis of the Bloch sphere. But the nuclear spin back of the substrate actually gives you the other axis, if you can characterize it. The way to think about it is you have some Rabi vector that you know how to implement, then you have some parasitic component on top of it. If you don't know what to do with this parasitic component, it's drifting on some time scale. It's going to look like noise. It's going to look like decoherence. If you do know how to characterize it, you actually just got another control knob. You can actually plug that into the timing of your sequence and actually use that for full control of the Bloch sphere. And that's what they did here. It's really a spectacular experiment, characterizing the substrate, the coupling to the noise in the substrate, implementing this Bayesian estimations involves a cosine multiplication, finding the maximum of a vector. All of this is done on the FPGA in microseconds. And then the analog feedback of generating the next sequence, taking this into account. So again, it's like real-time control with analog feedback, having the control system follow the qubit in time. Sorry. Now, the next example is from the quantum networking community. So quantum networks are about having qubits in different locations, being able to talk to each other, entangling qubits in different locations. So there are a few different paths forward for this. So what they do in this paper, I think it's pretty much a mainstream approach now. It's not the only approach, but it's a pretty popular approach. The idea is that you have local control of spatially separated qubits. So I've got a qubit in one building, a qubit in another building, and I've got an OPX on each one of those. I've got some control on each one of those. But then I have a joint measurement channel for the two qubits. So the idea here is that the entanglement is going to be created by projection. So I'm going to measure the qubits. I have one measurement channel for both of the qubits. So when I get a click, I know that the photon came from one of the qubits, but I don't know which one. And that measurement projects the qubits onto an entangled state. And then I can keep on doing local stuff. So I never have to actually directly couple them. The coupling actually happens via the measurement. Sorry. Now, the limitation of this method is that photon emission from these defects in the qubits, they're going to be stochastic. Okay, so the timing of the photon arrival is stochastic. That imprints a stochastic phase on my entangled state. Stochastic phases are not good for coherence. We want to know exactly what the phases are. And it's certainly not scalable if you want to entangle this pair and then that pair and then that pair ad infinitum. The stochastic phase will scramble everything to zero. So another problem is that we have inhomogeneous broadening. That means that each qubit actually sees a slightly different environment. And so you've got some random detuning in between qubits, and this detuning itself fluctuates on a time scale of about a millisecond. So this paper was all about how to compensate for these two things. So if you've got a stochastic phase, you can compensate with inhomogeneous broadening. You can compensate for that by echoing, okay, simply implementing a Hahn echo. But to do that, you need to know exactly what the timing is. How long do you want to implement the echo for? So that means that the photon arrival time, when did I get the click, it's not simply serving to trigger the next stage of the experiment. It's actually a parameter, a real-time parameter that's going to inform the next step of the sequence. So this was really quite an intricate paper, and it addresses some problems that are, on the one hand, these things sound very technical, but on the other hand, it's absolutely necessary to solve these problems if you want to scale up quantum networks. Now, my final example is my favorite because it's very technical and dry, and those are precisely the kinds of problems that we need to solve to scale up quantum computing. Because I showed a couple of really fancy experiments just now, but if you actually want to build a quantum computer, you need to solve a lot of problems that don't necessarily translate to high impact publications, because to succeed it becomes an engineering challenge. So the challenge that I want to talk about in this slide is scalable QPU initialization. So I briefly talked about the active initialization in the Ramsey example. So let's pose the problem. I spent $1 billion building a quantum computer. I've got hundreds of thousands of qubits. I'm putting this on the cloud, selling time on my quantum computer. I want this to be up and running as much time as possible. I don't want any downtime. I spent $1 billion on this thing. I want it generating value around the clock. However, we know that if I don't have any real-time feedback, then after each shot that my customer implements on the QPU, I need to wait 10 times that duration for the qubits to initialize. So 90% of the time, that's waiting for the QPU to initialize. Now, I mentioned one simple initialization method in the Ramsey protocol. So the way you measure a superconducting qubit, you send a pulse. The pulse bounces off a resonator and accumulates a phase from that resonator. And the phase that it accumulates from the resonator depends on the qubit state. So you've got the qubit, you've got the resonator, and then you've got my measurement. And this was an architecture that was hit upon actually over 20 years ago. And the idea is to isolate the qubit from the measurement channel. It's quite a universal problem in quantum computing. You want the qubits to be isolated from the environment to preserve coherence. But if they're isolated from the environment, how do you measure them? And if you could measure them very easily, that measurement is itself a noise channel. So with superconducting qubits, you have this really roundabout way of measuring qubits. You've got the qubit, you've got the resonator, then you're actually just measuring the resonator. And even the resonator is being measured dispersively. You're measuring it slightly off resonance because you're not looking at the amplitude of the transmission signal, but only at the phase. Anyway, that was maybe a little too much background, but the idea is that we get some phase from the pulse bouncing off the resonator, then we compare it to a threshold that is pre-calibrated, and then we know if the qubit is in the ground state or the excited state. Active qubit initialization involves comparing the qubits, the phase, the readout phase to this threshold, and then playing a conditional pulse with 120 nanosecond latency to initialize the qubit. If the qubit is in the excited state, I'm going to actively initialize. That sounds great. The problem is that in qubit measurement, we always have a limited fidelity. You never measure a qubit with 100% fidelity because we have a certain overlap between these two distributions. Okay, so if I measure a phase on one side of the threshold, it might actually be the tail end of the distribution of the other side of the threshold. So a typical readout fidelity might be, say, 98%. That means 2% of the time I measure my qubit, but I'm deducing the wrong result. I'm on the wrong side of the threshold coming from the other distribution. So if I want to initialize my QPU, the measurement fidelity will limit my initialization fidelity. I can have a million qubits, I'm initializing them with great latency, but 2% of them I'm actually misdiagnosing. And if you think about it a bit, it's actually impossible to correct even if you repeat this. Even if you take another pass to initialize all the ones you missed, that actually doesn't improve anything because the number of false positives is exactly balanced by the false negatives. 2% of 98 is 98% of 2, so they end up canceling each other out. So how can we overcome this initialization problem? So we can look at a more complex kind of initialization protocol. Okay, so this is a double threshold repeat until success protocol. So here we define two thresholds in the system. If I measure something to the left of P, then I know I'm in the ground state because the tail end of the excited state doesn't extend that far. If I'm to the right of A, then I'm in the excited state. So I'm going to play a pi pulse. If I'm between the two thresholds, I'm not going to play a pi pulse because I'm probably in the ground state, but I am going to measure again. And in fact, even if I was to the right of A and I play the pi pulse, I'm still going to measure again. So I measure again and again until I end up to the left of P. So it's a while loop. I measure this again and again. Sometimes I play a pi pulse if I'm to the right of A. Sometimes I don't play a pi pulse if I'm in between the two thresholds, but I still measure again and again until the phase ends up concretely in the ground state. So this gives me arbitrarily high fidelity. You can get essentially unit fidelity in QPU initialization, this method. But the problem is that it's not scalable. And the reason it's not scalable, this is now an interesting problem if we're thinking about how to build the control stack. Because imagine a million qubits. I've got this non-deterministic repeat until success protocol being implemented on all of them simultaneously. Qubit number 1 might be ready after 1 shot. Qubit number 17 might be ready only after 10 shots. So how do I know when my algorithm is ready to continue? I need to basically collect all this information in one place, and that is not scalable. I can't get a million qubit results into one place. That's something not scalable. I want to be able to make local decisions or semi-local decisions. Also, one qubit might heat up while it's waiting for another qubit to initialize. So this is very cool from an experimental viewpoint, but it's not the way to initialize a quantum computer. The solution to initializing a full-fledged quantum computer, this is by dynamically adapting the threshold. So the idea is that I mentioned that with the simplest kind of active reset, we don't improve measurement fidelity by repeating measurements. But that is only true if I do not update the threshold. If I measure the qubit once and I see the ground state, then the ground state distribution is effectively scaled to 97%, and the excited state distribution is suppressed. So now if I measure something to the right of the original threshold, it's actually more likely to be from the ground state, even though it's close to the excited state peak. It's more likely to be the tail of the ground state distribution, or vice versa. So the idea is that I can take, say, 5 measurements, and then I update the threshold each time, and the threshold on the 5th shot will be different if I measured a string of zeros, or if I measured 0, 1, 0, 0. It's also kind of Bayesian calculation. And this is scalable because it's deterministic. I pre-calibrate all these thresholds, and then I have local control. Each qubit undergoes, say, 5 or 6 of these shots, updating the threshold each time. And this is completely independent of what the other qubits are doing. And then after 5 or 6 shots, I know that all of my qubits are initialized to a certain fidelity. Now, this is A, deterministic, and B, high fidelity. Now, just to reiterate, I really like this example because it is so dry and technical. Okay, this is not going to be a Nature or Science publication, but you better be able to initialize a quantum computer with high fidelity if you actually want this to work. And also, this is something which we did not really plan on when we built the OPX. When the FPGA was being designed and Qual was developed, this is not a use case that we had in mind. But I mentioned that quant is very comprehensive. That really any kind of experiment you can think of is going to be manageable in quant. And I'll mention that this is because the way we implement a threshold, we don't really implement a threshold. If you look at any other product that I know of, the threshold that you use for state discrimination is implemented in a very special way. It's a privileged quantity. We define it, it's a threshold and nothing else. In qua, it's simply comparing two variables. You've got classical variables in qua. We populate one of them with the qubit measurement, with the phase. We compare that to another variable, which is the threshold. We can easily update that either of those variables in real time. So it's the fact that we're using a processor rather than test and measurement, a test and measurement product that makes this possible. So that was those were a bunch of examples just to show how real-time control is really vital for quantum computing, for like the low-level quantum computing architecture. We're looking at the control system as really being tightly integrated with the qubits, and the architecture of that quantum control system really determines what this quantum system can actually do. Now, in my last two slides, I want to talk about how we scale this up, some challenges involved in scaling up the quantum control stack, and I'll touch briefly on HPC integration as well. So we've got the OPX 1000. We've been shipping these in significant quantities over the past year. You can scale up a bunch of these chassis. So what requirements do we actually need out of a control system at scale? Sorry. The most obvious is synchronization. You need all these channels to be able to operate together. And this is really a unique challenge. Test and measurement companies have been shipping AWGs and so on by the shipload for years, for decades, but those are always operating small scale systems. If someone tells a test and measurement provider, I need like a million systems, not a million, but I need like 1,000 systems with 100 channels each, then those are going to be operating 1,000 separate experiments. A quantum computer actually needs thousands and many more, much more than that, channels operating synchronously. That's a new challenge. That's a new challenge. And that is a challenge that we believe we have a solution to. Another requirement is global data broadcasting. Okay, so I measure, that's something I touched upon in the OPX slide. So I measure qubit number 17 with this module on this chassis. And I want qubit number 25,001 to be able to access that information for its own purposes. That information has to be shuttled in between systems. And this information, I don't mean merely having separate systems trigger each other to start the next sequence at the right time, but the actual information, the actual real-time variables have to be shuttled in between. Distributed control and processing is another requirement of scale. By this, I mean, we don't want a central brain controlling the system, because a central brain is not scalable. The bigger the system gets, the harder it gets for the central brain to do anything. You want each one of these modules to have its own, so each one of these modules has its own FPGA, has its own processor. Now, when you have distributed processing, think of each one of these modules as being its own processor, and they can talk to each other. You don't need a central processor managing everyone. Each one of these processors can do its own thing and following its own local instruction set. And those instructions can include check what the other guy is doing, whether he's ready to continue, whether he got the results from his qubit, so I can use that in my own instructions. Okay, but there's no central processor running this whole thing. It's a whole lot of local instruction sets. Programming has to be scalable. This is something that the ecosystem is acutely aware of. So everything I just described now, this distributed control, the global data broadcasting, and so on, this can involve some major programming challenges if you don't have a good compilation process. Because if you want to send some variable from here to there, then how long will that take you? You need to wait for the register to empty, you need to wait for the variable to arrive, and so on. And the challenges that come from scale are simply insurmountable. The complexity is staggering when you scale up. You need some automatic compilation process to take all this into account, and that's something that we delivered on as well. So from the user perspective, you want to be able to program a 1,000,000 qubit experiment as easily as you can program a 5 qubit experiment. just copy paste, just write some macro that you repeat, and all of the complexity that comes from the fact that this at the end of the day has to reach a physical electronic system, all that has to be handled by a compilation process. Now, a couple less sexy challenges. So we need high channel density. Okay, so if you're an academic lab running a small scale qubit experiment, it doesn't really matter if the control system takes up this much space on the rack or that much space on the rack, and you'll manage. But if you're looking at something, data center scale, you want high channel density, and that's something that we designed with the OPX 1000. You need low heat dissipation. The bulk of the cost of ownership of a data center is the electricity bill, and they actually pay this twice. They pay the electricity bill to operate the GPUs and CPUs and so on. Then they pay it again because they have to cool it down. So they pay once to heat it up, then they pay again to cool it down. So low heat dissipation is really something that's built into the OPS 1000, something that we engineered into the system. There are unique components which are not commercially available that go into the system. And finally, HPC integration. A quantum control system has to be compatible with HPC, the HPC high performance computing supercomputers, essentially. There's pretty much a consensus in the community. I mean, it's like a blindingly obvious consensus that there is no quantum without HPC. Okay, quantum computers are not going to be standalone. They're going to be hosted in HPC centers, and they need to be tightly integrated with HPC. So that is really worthy of a session in and of itself. This is really, as I said, the future of quantum, and in quantum machines, they're putting a lot of thought into HPC integration, but I only have one lazy slide on it. So what will we do with a quantum computer in an HPC center? We've got piles of GPUs, piles of CPUs, and we ultimately want a QPU in there as well. So if you want to run some hybrid algorithm that has some classical stuff and some quantum stuff, you want to be able to jump in and out of the quantum computer, pass the information you need, pass the information that the quantum stuff needs, run some experiment, get the result, and then pass that back to the GPUs. You might also want to simply use the HPC to accelerate a purely quantum experiment, for example, optimal control, some kind of fast calibration, or even quantum error correction, syndrome decoding. That's too big for FPGAs, unless it's a dedicated FPGA, which is very inflexible and can't accommodate different codes. You'll need some GPU to implement decoding. So for that, you need to have fast communication between the control system and the GPUs. So this is, we have a very nice collaboration with NVIDIA to this end. And we demonstrated this in the IEEE in Montreal a few months ago. So a 3.4 microsecond round trip between the OPX 1000 and the DGX. So the DGX is the NVIDIA Grace Hopper, right? Lots of GPUs and CPUs that tightly integrated. And then we developed for them a server that can communicate with both the OPX 1000 and the DGX. And we benchmarked this by taking two numbers from the OPX 1000, sending those two variables to the DGX, summing them on the GPU, and then returning the result for the OPX 1000. It's a very simple benchmark, and obviously you can put very complex programs on the GPUs on one end and very complex stuff on the qubits on the other end. And that 3.4 microseconds, that's like the limit. That's the basic round trip latency. Now, this is really only possible when you have an instruction-based processor. If you imagine an AWG here, you won't be able to bring GPUs into qubit timescales in that way. Because what you can get from the GPU? It's going to synthesize a new kind of pulse. You need to upload that to the GPU. A minute later, you're ready to go. Okay, so you're doing things super fast on the HPC, but then you have this minute overhead until the control system is ready to go. This is only possible when you have a control system that follows instructions. So you only need to feed it a couple of variables, and then you can control the flow of the experiment. Now, another thing to think about in HPC and quantum is you need to be able to co-schedule these compute resources, not only for single jobs, but also between jobs. The way HPC centers function today, you send a job over the cloud, and so is everyone else. So my job might require 1,000 GPU cores and 10,000 CPU cores. And then at some point during my job, I'm not using all 1,000 GPU cores, I'm only using 100. So those 900 cores that I freed up can now be used by someone else. Someone else can jump in and use those GPUs. And there's a lot of scheduling software in these HPC centers. So how can we integrate a QPU into that kind of workflow? Okay, I've got a quantum computer in here. My job requires it for 10 minutes. And I've suddenly, now I'm not using my QPU anymore. My job is ongoing, but the quantum computer is only freed up. Now I'm only using GPUs and CPUs. Someone else has to be able to jump in and use that QPU. Even if I want to use it for 10 seconds, someone else wants to jump in for another second to use it, that has to be available. So again, falls into that. It's only possible when you have an instruction-based processor, so you can pre-compile instructions, and then you can achieve a millisecond dead times in between jobs. So that's currently where we are at. We've got millisecond dead times in between jobs. It sounds very technical, but it's really hard to imagine proper quantum and HPC integration without this. So that's what I wanted to talk about. I'll leave you with this image of just a layout of a classical computer chip. And really the take-home message here is that qubits are great, qubits are fun, qubits are awesome, but the control system is really the heart of the quantum computer. You can have the best qubits in the world, but the final actual computer will be severely limited unless you have the right control system on top of it. Yeah, so thank you. Oops.
Thank you. Thank you. Thank you. And Neil, Neil, did you see my chat message? You're up first for question. You have to unmute yourself.
Yes, and I have lots of things to turn on to do that. So my question is, why is repeated measurement with dynamic adaptation of the threshold considered deterministic? Why doesn't the repeated measurement simply tighten the tolerance each time you do the measurement, but never actually reaching a probability of 1 that you have the right value?
Okay, great question. Yeah. Okay. Good question, and probably some confusion caused by unclear terminologies. So you're correct that you won't reach unity. Okay, you can reach extremely high fidelities. I mean, you can simulate this and see that you can reach lots and lots of nines after the decimal point with this method. So it's functionally unity fidelity. It's not. I mean, nobody's going to worry. It's so close to unity that nobody's going to worry about how far it is from unity. When I say deterministic, what I mean is in terms of the number of shots necessary to reach that fidelity. The other method that we saw here on the right, the double threshold method, you can also reach a very high fidelity, but there's a non-deterministic number of steps. When you press play and you say, let's initialize the qubit, this might be implemented once, might be implemented 10 times. That's non-deterministic. The dynamic threshold, that is deterministic. You know you can implement 5 shots or 6 shots or however many shots, and you know that your fidelity is going to be what it is. Okay, so because it's deterministic, you know that the whole quantum computer, the whole QPU is going to be initialized with that fidelity after n shots, at the same number of shots. So you don't have qubits waiting for each other.
Thank you.
Other questions? I have a few, but I'll yield to anyone who has questions.
I have a question about the networking slide, that experiment.
Yes.
Yeah. So, is this a classic? We're using photons as qubits, and we're sending an entangled qubit from point A to point B via probably fiber cable.
No. So these are defect centers, like envy centers in a diamond or some such. Oh no, sorry. Here they actually used rare earths. So here they used erbium doping some yttrium crystal. Um, so these are solid state defects functioning as qubits. Um, and it's an optical experiment because these are measured optically. So you've got microwave control of the qubits. That's what the OPX is doing, controlling it via microwave. And the optical angle is the measurement. So you measure these qubits by um, basically applying an operation such that if the qubit was in the excited state, it's going to emit an optical photon, and if it's in the ground state, it's not going to emit that photon. So then you have a photodiode detecting that photon, and since in this setup you don't know which qubit sent the photon, you're projecting the two qubits under entangled state. So you've got spatially separated qubits, local microwave control, like electronic control of those qubits. Then the measurement, you've got some photodetector sitting there in between, getting one of the two optical photons, getting an optical photon of unknown qubit source, you could say.
Okay. But you're talking about two qubits that are separated by some distance.
That's right. That's right.
Okay, and so the information exchange is handled by your control boxes. I think you mentioned that each site would have one of your control boxes at each
Yeah.
location.
So this protocol requires some real time control. So basically, you wait for the detector to click. Once you click, then you've got some local control protocol before the measurement to prepare the qubits. Then you've got the click, and following the click, you've got some additional local control that you need to implement. So it's called entanglement distillation, usually in the literature, and
Oh,
that's the way
okay.
you end up with entanglement between spatially separated qubits. And that is being handled. Everything here is being handled by the control system. It's not something the qubits are doing on their own.
Okay. But your control boxes at each location are in communication with the other via classical
That's right.
networking or
That's right.
yeah, okay.
Yes,
All right.
that is correct.
Okay. All right. Thanks. Um, Question about your boxes in proximity to the qubits themselves. I assume they have to be in the same room or relatively close to the
Yeah,
cryogenic parts.
so you have SMA cables. You've got SMA cables going from these outputs to a cryogenic fridge. If it's an optical experiment, you might be going to AOMs and so on. Um,
Mhm.
SMA cables, you typically don't want them to be too long because you have parasitic capacitance and phase noise and loss and so on.
Yeah.
So it's typically a few meters away from the actual qubits.
And your equipment, you talked a lot about superconducting, I, um, which
Yeah.
could be Josephson junctions, and you also talked about vacancies in crystals. Are there other types of qubits like trapped ions, neutral atoms,
Okay. So
some of the
as the, yeah.
optical topological guys?
Okay. Okay. Good question as well. So the short answer is that we work with all these qubit platforms, but the value that we offer does differ between these different modalities. So with superconducting qubits and spin qubits, the OPX is really indispensable. Also with defect centers. Defect centers can also do some amazing things. With trapped ions and with neutral atoms, um, so first of all, they sound optical at first glance, but even if you have an optical setup with neutral atoms, for example, the laser is completely passive. The laser behaves almost like a local
Yeah,
oscillator in microwave experiments. You turn on the laser, you forget about it. All of the dynamical stuff that you're doing is via AOMs and EOMs and AODs and so on, and those are controlled via microwaves. So you have the OPX modulating AOMs, which modulate the laser. So we do work with those qubit modalities as well, but the value isn't as clear cut.
hmm
So let me explain why. So with optical tweezers, for example, the way you measure them is via camera. Okay, you've got some 2D array of atoms trapped in these optical tweezers, and then the measurement, it's not bouncing a pulse off of a resonator as I mentioned with superconducting qubits. you simply have a camera exposed for milliseconds taking a picture. And then what kind of feedback are you going to do on that? If you've got, okay. Oh, hearing myself and okay. Where was I? Right. So we're advertising like 100 nanosecond feedback, and that's really vital for superconducting qubits and many other qubit modalities. But if you've got a 10 millisecond camera exposure time built into your protocol, you're not going to pay extra money for those 100 nanoseconds. You may as well go to software. And with trapped ions is a similar issue. Trapped ions are extremely coherent. The gates that are applying to trapped ions are extremely long. So like a pi pulse can literally be a millisecond long. And they can simply go through software to implement this feedback. So when I show this picture of what a sorry. So when I show this picture and I say that the control system has to be tightly integrated with the qubits on hardware times, that is not necessarily true for trapped ions. With trapped ions, it can often go through software. So from a control perspective, it's very, very easy. The challenges of trapped ions, the reason they haven't won the race and they're nowhere near that yet, is because the challenges are elsewhere, not in the control system.
Thank you.
We have the usual question. And when I say the usual question, I mean, why don't we always answer this in the beginning of the talk? Someone posted in the chat, will the slides be available? If the answer is yes, then you can send them to me and I can make them available to our group.
Yeah, I'll send the slides, no problem.
Okay, great. Other questions? Well, if there are no other questions right now, then I want to thank you, Alicia, so much for this talk. Excellent, excellent presentation. And I want to make our members aware of the meeting that I just posted for February 11th. February 11th, I will be talking, yes, me, and what I'll be doing is a presentation on Grover's algorithm. It'll be elementary, completely elementary, too elementary for those who are already familiar with the algorithm. If you're not familiar with the algorithm, then please tune in. I'm going to be experimenting with a talk in which I describe the intuitive ideas behind the algorithm, and in addition, have everyone run quantum code in Qiskit on simulators and on real IBM quantum computers. And the experiment will be to see if we can accomplish all this, the presentation and the actual workshop, actual running of computer programs in the time allotted. I don't know if it'll work, but we'll give it a shot. So hope to see everyone on February 11th. Until then, stay warm, have a good month, and we'll see you in a short time.
Okay, thanks for the opportunity here, and have a good night, everyone.
Thank you.
Thanks, Barry, for organizing this. Thanks, Elijah, for a very fascinating presentation. And just want to let everybody know that if you have an idea for a talk, if you want to give a talk, reach out to us. We're looking for speakers. We're looking for subjects. Some of us like to talk, so all we need is an idea. So thanks for coming, everyone. And again, thanks,
like
Barry.
To talk and, we'd like to talk, and we'd like to hear other people talk.
Yeah. So.
See you again soon.
See you guys.
Neil in the chair has a question.
Oh, wait.
Oh, sure.
Well, I don't want to prolong your attendance, but if you're still around and don't mind answering another question, I have one, and it relates to where the code is executed. Is all this code that you're talking about actually executed on a microprocessor, or is some of the code some of the compiled code run in the FPGA, in the sense that the FPGA program gets changed from run to run?
Yeah. So good question. So the FPGA bit file is fixed. Okay, it's there's a processor architecture embedded on the FPGA. That processor has its own assembly language, and the core program is compiled to that assembly language, that instruction set. So from the user perspective, you can think of it as an ASIC rather than an FPGA. The reason it's an FPGA is that it allows us to update the processor. So we can always release new features and fix bugs and so on, and any systems in the field are always running the latest version. But from the user perspective, it's like an ASIC. If you had to flush an FPGA and upload a new bit file, it could take you half an hour to launch the simplest experiment. Right? I mean, you have a new idea for an experiment, you write a new program, it takes you half an hour between press and play until it executes. So that is not what's happening here. The FPGA is fixed, compiling to an assembly language. Does that answer your question?
It does, and thank you very much.
Thank you. Okay, we had the double goodbye, as Larry David puts it.
There we go. Do we have any other questions, or can you, if we do, can you hang out for a minute?
I'm here, sure.
Okay. Any other questions? Okay. Well, hearing none, I will bid you all a fond farewell, and we'll see you in February.
Good night. Take care.
Good night.
Good night.